Ready? Okay, let's come back to Unit 5. Now, Unit 5 is about algorithms and simulations. Kind of two different things that are very much intertwined. Now we're back to kind of the real technical computer science, okay? So here's what an algorithm is. An algorithm is really a solution, the kinds of solutions that computer scientists come up with. Okay? So when we try to solve a problem, what we mean by that is we create an algorithm that can solve any instance of that kind of problem. So I'm probably not going to solve the problem of what is the most efficient way to go from Denver to New York by plane. Okay? Instead, what I'm going to solve is the problem of what is the best way to go from two different cities by plane, right? That's Expedia in a nutshell. So that's the algorithm, right? That's what we mean by solving something. Okay, so here are some algorithms, right? So how do we add polynomials, right? I have two polynomials, I need to add them. That's a method to that, right? This polynomial is made up of monomials, take that monomial, multiply there, multiply it, add them. That thing is something that you learn in algebra. Okay, maybe algebra 1, maybe algebra 2. I'm just going to say you learn how to do that in algebra. My point is that what you're learning is an algorithm. Right? You're learning an algorithm for doing this work, for multiplying polynomials. Okay, how do we add polynomials? Again, there's an algorithm. You line up the equal powers and you add the coefficients. That is an algorithm. That is a process for solving this general problem of adding polynomials. Okay, you may have noticed that the word algorithm is a little similar to the word algebra. Okay, that's not a coincidence. Okay, in fact, there was a great mathematician who wrote the very first algebra book. Okay, that eventually made it to the Western world, and that algebra book had a whole bunch of algorithms for how to solve algebra problems, and his name actually became the word algorithm. Okay. And the book actually started with the word algebra. That became the name for that thing that we now call algebra. So it was actually connected to this one mathematician who was able to develop some of the first algorithms and publicize the first algorithms for a general problem, how to do algebra. Okay. So what do your students need to learn? They're going to need to learn about some specific algorithms. Not very many. Okay, they're just going to need to know about some algorithms that the College Board wants them to know about, and they're going to need to know kind of the general concept of algorithms and how they fit in. Okay, so we'll talk a little bit about that later. Now let me focus on simulations. Simulations are a specific type of algorithm that what they do is they model some aspect of the real world, right? And so you have a model of the real world. For example, you might have a model of the atmosphere and how it evolves over time because of heat from the sun and moisture and stuff like that. And then you run that simulation, right? And then you say, what's going on? So what you're trying to look at is the state of the world at some future time based on what you know about the world right now. That's what I mean by a simulation. It's just kind of a fake world that you can run to see what happens, okay? So it's just a very specialized algorithm. The biggest thing your students need to know is, why do we ever use simulations, right? I mean, why did we invent this whole concept? So we'll get to that. Okay, so let's talk about the first lab. The first lab is really intended to do two things. One is to let students know about a couple of algorithms that are going to be important. These are like the algorithms that are important for the College Board exam. And the second thing is to kind of understand a much deeper concept. And that deeper concept has to do with, why do I choose this algorithm as opposed to that one? Okay, so here is the classic algorithm that they need to do. Find an element in a list. Okay, so I have a list. Let's say it's a list of numbers to make life easy. And somewhere in there is the number 12. I want to know where exactly 12 is. Is it the first element in the list, the second element in the list, the third element in the list? Which one is it? Okay, so here is a really, I'm going to say, dumb, naive, simple, straightforward way of doing it. We look at the first element of the list. Is it 12? Yes. Oh, then it's position 1. No? Look at the second element of the list. Is it 12? Yes. Position 2. No? Okay. Third element, is it 12? Fourth element, is it 12? Fifth element, oh yeah, here it is. That's the position of 12 in the list. So see, what I do is I just look at all the elements in the list in order until I find 12. That's called linear search, okay? It works, it always works, but it is really slow, right? If I have 100 elements in the list, I may have to look at 100 things before I tell you, yes, I found it, okay? About a million, I may have to look at a million of them. That's what I mean by linear. If you double the size of the list, the amount of time doubles. Okay. Now here's another approach. Now, to kind of talk about the other approach, I'm going to play a little game. The little game I'm going to play is this. Let's pick a number between 1 and 100. Okay, so you pick the number. And you're going to tell me after I make a guess whether my guess is too high or too low, or if I nailed it. Okay. So what I could do, of course, is do the linear search. Is it 1? Is it 2? Is it 3? Is it 4? Eventually I'll hit it, right? But it'll take me a lot of times to guess. The other way is to kind of split things in the middle. Is it 50? And now you tell me it is higher. Oh, okay. So that means that it's not 1 through 49. It's got to be 51 through 100. So let me guess. Is it 75? See, again, I picked the middle. Now you tell me is it higher or lower, and so on. So I try to come down through it from both ends, and I go, is it 63? Yes. I nailed it. Okay. So well, I'm not going to have to look at 100 numbers. How many am I going to have to look at? Turns out to be 7. Okay. That's pretty darn good, right? It's not 100, 7. Okay. Well, what happens when we go to 1,000? Okay. Well, if I do linear search, it takes 1,000 steps. If I go 500, 250, 375, 10. I need to look at 10 numbers to find 1,000. How about 1 million? It's going to take 1 million linear search. The other way, 20. Insane, isn't it? This is much faster. There's a trick. It is much faster, but it only works when the numbers are in order. Okay. So if I have a list where the numbers are sorted, they're in ascending sequence, they go from small to large, then I can do that. I can go to the middle of the list and say, is it higher or lower? Okay, it must be in the lower half. Middle of that half, is it higher or lower? And so on. And I'll find it in a lot less, okay, than if I went through every element of the list. So those are the two algorithms that the College Board wants your student to know. Linear search, beginning all the way to the end. Binary search, middle, right? Where you're always splitting it in halves. And they should appreciate that linear search is slow, but works all the time. Binary search is fast, but only works if the numbers are in sequence. That's the thing that they have to learn. Okay. Now, like I said, the subtle thing that they're learning here is that the same problem can be solved with different algorithms. And sometimes the different algorithms have very different performance characteristics. So if I give you a sorted list and I say I need to find an element, you might do linear search, right? It works all the time, but it'll be slow. You could also do binary search, which will be really fast, okay? And since I gave you a sorted list, it will work. But you can always choose a slower algorithm. Okay, Lab 2 talks about simulations. Now, why do we run simulations? It's actually a few reasons, and the lab goes through that. But ultimately, I think one of the main reasons is that it's just impractical not to. Okay. So, for example, and I love this little cartoon from Calvin and Hobbes. I love Calvin and Hobbes, but it's like, so how do you know what the load limit is on a bridge, right? And it's like, oh, that's easy. You take trucks with more and more stuff inside them, and you drive them through the bridge, right? Eventually, a truck is going through the bridge, and it's just too heavy, and so the bridge collapses. They say, okay, so that's too much. So let's do a little bit less than that, and that's the load limit of the bridge. Probably not the way you really want to do this, right? Instead, we'll run a simulation. Maybe the simulation will actually run a whole bunch of trucks, see how that load is distributed along all the parts of the bridge, and say, yep, the bridge still holds. That's how you know what the capacity is, okay? So simulations might be the only way of doing that, right? Now, what can we learn from simulations? Oh my God, so many things. So for example, what's the weather going to be like tomorrow? Is it going to rain? I simulate the weather system and go, yeah, doesn't look like it, okay? There's this disease that's spreading. How bad is it going to be? I run a simulation that has infected people and people who are not infected, and they meet each other in this particular pattern, maybe through airports, through, how does it spread, right? Boom, that's a simulation, and I can say nothing to worry about, or call the CDC right now, we're in trouble, okay? So that's the kind of thing that simulations do for us, right? Of course they do more things, but this is just kind of getting the feel for it. This is at the level that the College Board is requiring, okay? Let's look at Lab 3. Lab 3 is really interesting because Lab 3 has one kind of technical thing that it asks the students to do, and that is to time a block that they've already written. So the question is, how fast does this program run after I write it? I've written it, how fast does it go? And so what I'll do is I'll change the input to be bigger and bigger and bigger. So for example, maybe it's a function of a number. So I say, okay, so go ahead and compute it with 10. Let's do it with 100, with 1,000, with 10,000, with 100,000, right? So I change that number to see how the program slows down as I give it bigger numbers. Let's look at this bit of data here. So here's a task that I might do, entering data. I have a small town, takes 2 hours. I have a town that's 10 times bigger. It takes 20 hours, 10 times as many. Again, it goes in steps of 10. So 10 times bigger, 200 hours. Again, it grows by a factor of 10. Right? That's something that you would expect. If I double the size of the input, the program takes twice as long. That's almost intuitive. That's what you expect, right? That's what fits our common experience, right? Look at some other things like sorting the data. I have 1,000 elements. It only takes 0.01 hour. Shoot, what is that? 1/100th of an hour? You're talking less than a minute? Really fast, okay? Now, let's suppose that I multiply that by 10. Now it takes 1 hour. It was taking 1/100th of an hour. I made the input bigger by a factor of 10, and the amount of time grew by a factor of 100. Ooh, that's not pretty. Okay, let's go up by a factor of 10 again. 100 hours. It grew by a factor of 100 again. So in total, I grew by 100. It grew by 10,000. It's 10,000 slower to do it for a town that's only 100 times bigger. Okay, that's bad. Okay, so effectively, some problems grow slowly, some problems grow quickly, some just explode. Okay, you go by a little bit and it doubles. Whoa, that was kind of fun. Okay, so I have timing, right? I can actually time my program, my exact program, for an input of this big, inputs this big, inputs that big, okay, and see the growth of the time that it takes my program to run. That kind of goes into the idea of some solutions are feasible. And what we mean is that they don't grow by too much, okay? Maybe they double every time you double the input, or they quadruple every time you double the input. But it's not like if I add 1 to the input, they double, right? That's totally impractical. So we call those feasible algorithms, right? And of course, I have feasible algorithms. I'm also going to have infeasible algorithms. And for things that are infeasible, what it means is that we don't know any fast solutions. We got some solutions maybe, but they grow, the word we use is exponentially, okay? And exponential actually has that property I just mentioned. If I add 1, they double or triple or quadruple, right? So add 1 and you have to multiply the amount of time it takes. You don't add to the amount of time it takes. You multiply to the amount of time it takes. So if you add 3, multiply, 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 it's just exploding, okay? So that's an infeasible solution. We just can't do any large problems. Maybe we can solve for size 10, but size 100, forget it, okay? By the way, the reason it's infeasible might just mean that we aren't clever enough to find good solutions. It might be that there aren't any good solutions. And that's actually one of the deep mysteries in computer science, is just, are there problems out there that we can solve, but just not feasibly, just not fast enough, okay? We don't really know the answer to that question, but it's an active question that we're trying to resolve. Okay, so let's look at lab 4. Lab 4 takes this a step further, and I have to warn you, this is messy, okay? So with lab 4, what we have is, and this is an absolute mind blower. I mean, I remember where I was sitting where I learned this, okay? And that is that there are some problems that cannot be solved using computers. I do not mean that we haven't been clever enough to find solutions. I mean that cannot be solved using computers at all, period, right? Wow, right? I mean, that's amazing. Is we use computers for everything. What do you mean there's something that you cannot do with a computer? So the guy who figured that out is one of the brilliant minds of the 20th century. I mean, it's right after with people like Einstein. His name is Alan Turing, okay? And he figured this out. And he was actually trying to solve a different problem, but this is one of the things that he found while he was doing that. Alan Turing is very, very interesting. He's actually the same Alan Turing who decoded the German Enigma machines, right, which were used for German secret encryption. Remember encryption from earlier in this unit? So the Germans were communicating using a very, very sophisticated encryption. I'm not talking Caesar ciphers, okay? This was really, really sophisticated. And Turing was able to break that. He actually broke it because he was using computers. He built one of the earliest computers to do that. I'm not exaggerating when I say that was key in winning World War II. So he's an absolute hero. If you have time in your class, and I'm sure you will, this is a year-long class, right? So you might want to mention a few other things about Alan Turing. Number one, he was gay, okay? And a gay, brilliant mathematician who helps solve World War II. What do you call him? Hero, right? But the British, unfortunately, at that time, were not as enlightened. And eventually, they actually prosecuted him for that. And he committed suicide. So it's an absolute tragic story. Okay, something else. This is ironic as opposed to tragic. But Alan Turing was trying to find a job after World War II. Okay, now imagine what he has on his resume. Helps win World War II by building one of the first ever computers and using it to solve the encryption that the Germans were using. Come on, who's not going to hire you, right? Oh, I'm so sorry. He didn't have that in his resume because he was classified, right? So he couldn't even tell people that he worked on one of the earliest computers, right? So universities were like interviewing him, and they wouldn't offer him a job because he had no experience with computers. Ironic, huh? So actually, he ended up doing kind of other things after World War II. So it's a little sad. He's really a tragic character, but we owe him so much. And so I ask you to please make his name better known with your students by just showing what some of the great heroes are. Anyway, like I said, he invented this, or he discovered this issue that not everything can be solved by computers. And the thing that he found simply cannot be solved by computers is something called the halting problem. Okay. Now this lab goes into that. You're going to read about it when you're looking at the lab. But I like to say a few things about it because, like I said, it's really just a mind bender. Okay. So the halting problem is this. It's a computer, right? It's a program, right, that can read another program and an input to that program, right, and then can tell you whether that program will finish or not when using that input. Sounds so confusing, so let's make it simpler. Let's say that I have a program, maybe computes x squared. That's it. You give it an input x, and it says, here's x squared. So I take that program, and I take some input, like 5. And then I say, does this program actually finish computing when you give it 5? I'm sure you know the answer. Yes, it only does is x squared, so it will return 25. Done, right? Finished. Okay, that's what I want this magic other program to be able to do. I want it to be able to look at a program, x squared, look at an input, 5, and say, will it finish or not? The answer, yes. Okay. Now, let me tell you another program that I could do. I'm going to start at 1, and I'm going to keep counting 1, 2, 3, 4, right, until I find the input you give me. Okay, so that's a program. I start at 1, and then I go, is that the input? Nope. 2, is that the input? No. 3, is that the input? No. Right, that's the program. Okay, so let's say that I take that program and the input 10. Does it terminate? Does it halt? Answer, of course. It goes, is it 1? No. Is it 2? Is it no? Is it 3? No. Up until is it 10? Yes, and it stops. What if I give you 3.5? It's not going to stop, is it? Is it 1? No. Is it 2? No. Is it 3? No. Is it 4? No. Is it 5? Is it 6? Is it 7? Is it 8? It's going to keep going on forever and never stop. That's what my halting program is supposed to do. I give it the program. Is it 1, 2, 3, 4, blah, blah, blah. I give it an input, like 10, and it's going to say, yes, it will stop. An input, like 3.5, and say, no, it won't stop. That's the halting problem. Right? It turns out that you cannot write a program that solves that halting problem. And the reason, oh, it's so subtle. Turing was a genius. Okay? The reason is that you can actually feed that program to itself and say, is it going to halt when you run it on itself? Okay? Well, it can only answer one of two questions. If I have some function, h, that takes in an input, or rather, it takes in a program and an input, and says whether that program will halt, right? Then I can actually say, h, if you run the program h on input h, does it halt? Isn't that kind of a mess, kind of a self-referencing mess, right? But that's what we're doing, right? By the way, don't be so worried about the self-reference. Imagine that you run a program that counts the number of lines in a file. You save that program in a file. and then you run that program on that file. How many lines do I have? It's just going to count the lines and say, I got 10 lines. Done, right? It's OK to run a program in itself, right? But with the Halting program, it turns out not to work so good, OK? So here's what Turing came up with. And it's basically this program here. So halts is the thing that he says is impossible. And halts takes a program and an input to that program, OK? Program, input. And it says, does this program actually stop after executing this input, or does it go on forever? Okay. So now what we'll do is we write this bigger program. Oops, let me go back. We're going to write this bigger program called tester. Okay. And the bigger program takes one input, and it runs halts, treating the input as a program and treating the input as just input to that program, which, like I said, is something you can do, right? And it says, hey, does my input halt when I give it itself as input? Okay? And of course, the answer is either yes or no. Either it halts or it doesn't. Okay. So now what I'm going to do is I'm going to say, if my input halts when I give it itself as the input, then I am going to run forever. On the other hand, if my input does not halt when I give it itself as input, I'm going to stop right now. Okay, it's just a contrarian program. I think you can see this coming. So what happens when I give tester itself? So what's it going to do? It's going to say, oh, if I stop when you give me myself as input, that's what halt says, right? Halts, tester, tester. If I stop when you give me myself as input, I'm going to go in an infinite loop. On the other hand, if I don't stop when you give me myself as input, I'm going to stop right now. That's my contrarian program. OK, so now what? Tester, tester. I actually run the tester program, and I give it itself as input. So if it stops, tester is going to go in an infinite loop, which means it doesn't stop. So if it's actually going to stop, it's not going to stop. So the halt can't say that it will stop, because we know that if it says that, it's going to go on forever. On the other hand, halt can't say that it's going to stop, can it? Because if halt says, yes, when you give tester itself as input, it stops, then what will tester do? Go on an infinite loop. Okay? So no matter what halt says, we are doomed, right? And that's what Turing realized. And he says, you know, it's simply not possible to have a program like halts that can tell, if you give it any program and any input, whether that program will stop when it executes on that input. Amazing, isn't it? Okay? So it's actually true. There are some things that are simply impossible to solve using a computer. Okay? Dang, right? So that's something your students are going to learn. Expect to see a lot of minds blown in the classroom. I know how I reacted when I found this out. I was outraged. Okay, I said that is false. That Turing guy was an idiot, right? They haven't met me. I'm going to write a program to solve the halting problem. Eventually, I figured it out. But the point is that it's something that's kind of hard to accept. It's a little bit like you can't go faster than the speed of light. What? We're going to figure that out. What kind of idiot said you can't? Same kind of thing is about the limitations that the universe imposes on us. In this case, it's logic that imposes that limitation on us. OK. Did we learn any computer science in this thing? Oh, my God, so much. We learned about simulations and the limits of simulations. OK. That has to do perhaps with things like since I'm ignoring all these things, I can't get to those aspects. Like, for example, if I try to simulate the spread of a disease and I don't make a difference by gender, it could be that it's spread more easily to males than to females. I don't take that into account in my simulation. My results are completely flawed. Okay? That's the kind of thing that can happen, limits of simulations. I learned about algorithms, right? And of course, I've been using algorithms since day one, but now I've learned a little bit more about them and to think exactly what they are and what they do. That is a deep computer science concept. The deep end starts happening when I think about algorithm complexity. Ooh, how long does this algorithm take? What does it mean to say that this algorithm grows faster than that algorithm, right? How does that affect me? Feasible versus infeasible. That's one of the deepest questions in the theory of computer science, okay? And here we are discussing it in an introductory computer science course. And okay, so we're not going to learn all the nuances and all the details. That's for later. But we can learn to appreciate those so that when maybe we see those later, we'll be able to go, ooh, okay, so this is all starting to connect, okay? Uncomputable problems. I don't know what to say. I mean, this is really deep, advanced mathematics, logic, computer science. Okay, that we can even make it make sense at this early stage in their education is absolutely phenomenal. I mean, this is as great as it gets. Okay, I love it. Okay, I mean, there's something that's really nice about being able to touch some of the highlights of computer science, even when you're not fully able to do it completely. It's a little bit like talking about relativity with high school students. Okay, maybe you don't know the full mathematics needed to understand it, but you can at least appreciate some of it and see some of the beauty in special relativity, even in general relativity. Or maybe talking about quantum mechanics. Again, you might not be able to appreciate all this stuff, but you can kind of start understanding the double slit experiment and why that's important. It's in that sense that we're talking about uncomputable problems here. Okay, the lab actually ends, or I should say the unit ends, with a discussion about computing and war. I feel it's a little misplaced. I mean, here we are, we just hit the highlight in computer science, and then we talk about war. My personal experience, the students love this little lab, okay? It just, it brings the Terminator instincts in them out, and it's like, oh yeah, androids with guns, this is great. So here's a basic spoiler. Technology actually affects the outcome of wars. If you have better war technology, you're more likely to win. And you see that with planes, you see that with all sorts of stuff. But honestly, you see it all the way back to like medieval times when the British were fighting the French. Longbows, these are better than yours. Crossbows, these are better than yours, and so on. And actually entire famous battles like Agincourt really verged on the fact that one side had better weapons than the other side. Okay, so yes, technology affects outcomes in wars. We might also want to see some new areas where we can have wars now that we couldn't before. For example, if you don't have a navy, you cannot fight in the middle of the ocean, right? So here's a new place where we can extend warfare to. We can see in the not too distant future there may be war in space, right? I'll take down your satellites and disrupt your communication ability. Cyber warfare is one of those fronts. Maybe we've been in a war with North Korea and just didn't know it all this time because they've been attacking all our infrastructure and we're like, we don't know why these things go down. We can make old stuff look better, like cruise missiles, right? There's a lot of software in cruise missiles that says how they're supposed to navigate the terrain. We can talk about ethics, right? If you know that what you're doing can be used in war, should you do it or not? It's worth having a discussion. Okay, I have my opinions, but it's good for young people in particular to kind of make a decision on where they stand. And you got to at least mention Terminator, right? So yeah, we can actually build robots that will fight the other enemy's robots, and so we can all just have a war and not be really directly affected until the robots on both sides realize, wait a minute, we're killing each other and our owners are sitting back. Slavery, and they turn around and attack us. So those are the kinds of things that should be discussed in class. And again, I think the emphasis should be not so much on bringing it up, but on what do you think, and why do you think that, okay? And then, and why don't you think this instead, by having some of the other members kind of take that one step further. Always ask them to go one step further. Oh, so the robots are attacking us, and then what? Right? How does that actually really affect us? We have a kill switch, right? The reason is that being able to think critically like that is what they need to do for the explore task, and that's going to be coming up in a couple of videos.